Hi guys, welcome back to the channel. In this video I will be going through amines, and this is from the A-level chemistry curriculum. So let's begin. So first, looking at making primary aliphatic amines. So these can be prepared by undergoing a nucleophilic substitution reaction of ammonia with haloalkane. So looking at my haloalkane, so I've got bromo, ethane in this case, and I've got ammonia. So what would happen now? So the bond, the carbon which is bonded to the bromine, so this would be delta positive, because bromine is more electronegative than carbon. So now what would happen is the lone pair from the nitrogen would be attracted to that carbon which has a delta positive charge, and this would end up forming a bond like it can be seen here. So now we have a bond formed between nitrogen and carbon, but as you can see, the nitrogen has a plus charge and the nitrogen wants to get back to its neutral charge. So now what can happen is another ammonia can come along, and it can take one of the hydrogens, and the bond which is between the N and the H, so this will break, so the electrons from that bond will be given to the nitrogen, so that the nitrogen will end up having a lone pair in here, and it will also end up having that neutral charge again. So this is nucleophilic substitution reaction of ammonia with haloalkane, and the conditions, just a reminder, so this happens in a sealed tube with ethanolic solution. So if we were to look at the equation for this, so first we start with our haloalkane, so in this case it was bromoethane, and now we add ammonia to this, and we would end up forming an amine as well as ammonium bromide. And to balance this, you would just simply add 2 in front of the NH3. Okay, so now looking at nucleophilic substitution of haloalkane with HCN. And this would happen under reflux and ethanolic conditions. So as you can see in this diagram, so we have our cyanide ion. So this is from the HCN. So now what can happen is it can simply, that lone pair can simply be attracted to that delta positive carbon again, and now again that would be forming a bond with the CN, and this would be kicking off the bromine. So we would end up having a CN there and H as before, the hydrogen stay on there. But now this is still not an amine. So what can now happen is these nitriles can be reduced to form amines. So reduction can occur, and there's two types of reduction. So first we can have the non-selective reduction, and this is by hydrogen and a nickel catalyst, and this happens under a high temperature and a high pressure. So as you can see in the equation, so we first have that nitrile, ethane nitrile in this case, and we simply just add hydrogen to this, and the reduction reaction occurs, and we end up forming an amine. In this case we have ethyl amine, as it can be seen here. Just to remember that this is non-selective reduction, so if there was to be a double bond in here, then that would also be reduced. But now looking at the selective reduction, so in this case we have the for the reagent we have the lithium aluminium hydride. So from this we end up getting a hydride ion, and the conditions for this is ether. So ether is basically a organic compound. You don't need to know much about this, but that's just the condition for this. Looking at the equation, so we have ethane nitrile again, and to represent our reducing agent we can have a H and square brackets around it, like you can see here, and this would end up forming ethyl amine again. And to balance this equation we could just add 4 in front of the H. So looking at this way of producing amines, so going from haloalkanes and then to nitriles and then to amine. So this can be a more useful way because in this the carbon chain is extended by one carbon. So because we're adding that cyanide, so CN, and that would end up extending the carbon chain by one, and this can be really useful in organic synthesis. So now looking at producing aromatic amines. So aromatic amines can be produced by reduction from nitrobenzene. So looking at nitrobenzene, so this is an aromatic compound because this has a benzene ring in it. So we have nitro group here. So what we can do is we can reduce this, and then we end up forming this phenyl amine, as you can see here. And this again is an aromatic compound because it has a ring in it. So how does this happen? So looking at the reagents, so we can add HCl to it, as well as a tin catalyst, and the conditions would be high temperature and high pressure. So looking at the actual equation, so what happens is we have that nitrobenzene at the start, and as before we add that reducing agent. So in this case this was HCl, so I can just represent this by having H in square brackets. So then we would end up forming our phenyl amine. So replacing the NO2 with a NH2, and we end up forming 2 molecules of water from it. And to balance this, we can add a 6 in front of the H, and this would end up balancing this. Now, just as a note, in some of the exam questions you can have 2 nitro groups in one benzene, so just adapt your equation accordingly. But you also just need to be aware that aromatic amines, so like the one we can see here, so which are prepared by the reduction of nitro compounds, so these can be used in the manufacture of dyes. So remember to say that they can be used in the manufacture of dyes instead of saying that they can be used as dyes, and there is a difference between them. So aromatic amines can be used as manufacture of dyes. Okay, so now looking at the basic properties of amines. So amines can act as bases by accepting H+. So this is simply because they have a lone pair of electrons which can attract H+. So aliphatic amines, they have an inductive effect. So what this inductive effect does is it makes the nitrogen a little bit more negative, and it just means the electron density will be greater on the nitrogen. So looking at an aliphatic amine, so this is a primary amine because we have a carbon bonded to the nitrogen. So what does this inductive effect do? So what this simply does is the electrons in that CN bond will be pushed towards the nitrogen simply because nitrogen is more electronegative, and this just means that nitrogen will be even more delta negative now. So comparing this to ammonia, so ammonia does not have a carbon attached to it, so it will not have that same inductive effect as that primary amine does. So in that case, that primary amine, so the lone pair of electrons would be more available. So as you remember, there will be lone pair of electrons on the amine, and because of that inductive effect, the primary amine will have the lone pair of electrons more available than ammonia. So this is just the inductive effect. And the longer carbon chains have greater inductive effect. So in this case, this was only a methyl group, but if we had an ethyl group, this would have a greater inductive effect. So secondary and tertiary amines have more carbon chains, so this just means they will have a greater inductive effect. So looking at dimethyl amines, so instead of having one methyl group attached, it has 2 methyl group attached. So this just means that electrons will be pushed from both ends, so this will make the nitrogen even more delta negative, so the lone pair will be more available. And this will increase a little bit more for the tertiary amines because the electrons will be pushed from 3 sides now, and that will have the lone pair of electrons most available compared to the dimethylamine and the methylamine. So looking at aromatic amines. So aromatic amines are weaker bases than the aliphatic amines we've looked at. And this is because the electron density on the nitrogen is a little bit lower compared to the aliphatic amines. And this just means that a lone pair on the nitrogen would be less available. And this is due to the delocalization, which we'll look at now. But this is a phenylamine. So phenylamine would be a weaker base than the aliphatic amines. Now this is simply because the lone pair on the nitrogen, so as we can see here, so this becomes part of the delocalized system. So we have delocalized electrons inside and that benzene, and the lone pair on the nitrogen becomes just part of that delocalized system. So this just means that that delocalized pair of electron is less available for attraction. It's less available to attract a H plus ion, and this is why the aromatic amines are weaker bases. So just comparing the strength of the bases now. So the aromatic amines would be at the last, so they are the weakest bases, and then we could have ammonia, and then primary amines, secondary amines, and then we could also have tertiary amines after that. And also remember that if we have a bigger carbon change attached to the nitrogen, so instead of having an ethyl attached, if we have a butyl attached, then that would also cause an increase in base strength. So looking at the nucleophilic properties of amines. So amines have a lone pair of electrons on the nitrogen. So this just means that they can act as nucleophiles. So just remember that nucleophiles are just electron pair donors. So looking first at an ammonia molecule, so what can happen is a haloalkane can come along, and that ammonia can react with that haloalkane in a nucleophilic substitution reaction, which we have looked at earlier, and this can end up forming a primary amine. Now that nitrogen still has that lone pair of electrons. So what can happen is that another haloalkane can come along, and again, nucleophilic substitution, and we've ended up forming a secondary amine. So again, we have a lone pair on the nitrogen, and this can happen again, and we end up forming a tertiary amine. And then finally, that reaction can occur again, and now we end up forming a quaternary amine. So now the reaction can no longer happen because we don't really have a lone pair left on the nitrogen. Remember that we were getting the lone pair from the hydrogen which was bonded to the amine, but now because we don't have any more hydrogens bonded to the amine, so we're not able to get that lone pair back, and because of this we will have a plus charge on the nitrogen. Now because of that plus charge, so because we were reacting that with a haloalkane, so the haloalkane we were reacting it with, for example, if we were reacting it with bromine, so that would end up having a minus charge. So these two can be attracted because one is plus and one is minus, and now what we can say is this has formed a quaternary ammonium salt. And in this case, we can say that this would be a quaternary ammonium bromide salt because we have that bromide in there. Okay, let's just say that I want my main product to be a primary amine. So what I can do is I can have the ammonia in excess, or I can limit my haloalkane. Now this is because if I have my ammonia in excess, this just means that we will run out of our haloalkane before we can go to any further nucleophilic substitution reactions, and that's why we would end up forming a mostly primary amine. If I want my main product to be my quaternary ammonium salt, then I can have my haloalkane in excess, because if I have my haloalkane in excess, this just means that until we have formed our quaternary ammonium salt, and the further nucleophilic substitution reactions would keep occurring until we have eventually formed that quaternary ammonium salt. And you also just need to be aware that quaternary ammonium salts can be used as cationic surfactants. Please just be aware that ammonia and amines can undergo nucleophilic addition elimination reactions with acyl chlorides and acid anhydrides. So if that reaction was to go ahead, so acyl chlorides with ammonia or amines, then we end up forming an amide, and in the case of amines we end up forming an N-substituted amide. So for example, we have an acyl chloride there, ethanol chloride in that case, and we have our primary amine there. So as we know, that carbon would have a delta negative charge because it's bonded to an oxygen. So what happens now is the lone pair from the nitrogen will be attracted to the carbon, which is bonded to the oxygen. And what happens now is the carbon would double bond oxygen, so a curly arrow would come from that and it would go into the oxygen. So now looking at the next steps, so if I were to draw my acyl chloride now, so I have that C double bond O, it'd be a C single bond O now, because now that an electron pair has gone from the double bond into the oxygen, so this would have a lone pair now, and this would have a negative charge, and this is bonded to a CH3 and as well as a Cl, and now this is also bonded to a nitrogen with 2 hydrogens and again a methyl group. So there will also be a plus on the nitrogen, and what can now happen is we can end up forming that double bond again. So there will be a curly arrow going from the lone pair on the oxygen into the single bond, and that would be forming a double bond. And now because that carbon would have 5 bonds, so what it wants to do is it wants to get rid of that chlorine. So we would get rid of that chlorine, and also the nitrogen wants to form a neutral, wants to be neutral. So what can now happen is I can kick off one of the hydrogens like this, and we have now formed our N-substituted amide, which in this case is N-methyl ethane amide. Finally, our acid anhydrides could react with ammonia or amines, and these would also end up producing amides in the case of ammonia, and N-substituted amides in the case of amines, and also an acid. So taking an example, so we have ethyl amine in this case, so this is reacting with a methanoic anhydride. This ends up producing our N-substituted amide, which in this case is ethyl methanamide, as well as our acid, which in this case is methanoic acid. In this case, you don't really need to know the mechanism, but you just need to be able to write equations for this reaction. Thank you so much for watching this video. If you did like this video, don't forget to subscribe to see more of these, and you can watch my recent videos by clicking on the links popping up. Thank you.